Welcome, Questiongoddess. We'll name ourselves at the end of this video, but I'm here to talk about the theories of relativity. Notice I say theories because there are two, and me and my SpongeBob um, bandana will talk about them today. So there is special relativity and general relativity. Special relativity is what everybody thinks of when they think of Einstein. E equals mc squared, which we will talk about later. But special relativity also states that the laws of physics are always going to be the same. That's why they're laws. They're always and always accepted as truth, that the laws of physics are always the same. So the speed of light in a vacuum is the same for all observers. So say here's a planet, there are observers on both. Okay? And I'm a source of light and we are in space right now. Woo! Insert Doctor Who theme song. Okay. So let's call this one Jean-Luc Picard and James Tiberius Kirk. So Jean-Luc Picard is right here, and James Tiberius Kirk is right here. Well, they're both at different distances from me, the source of light. So you think that because they're in different spaces means that my light is going to hit them at different times. But no, because there is limited space time in a vacuum, like space, the speed of light will move at exactly the same time, reaching both of them at precisely the same time. So, it is impossible to say that two events occur at the same time if they both occur in different spaces. So, let's say Jean-Luc Picard is in Starship Enterprise and is orbiting around Earth. Well, Captain James Tiberius Kirk is back on Earth doing earthy things. But right now, it's noon as they perceive it, and they're both brushing their teeth. I don't know why they're both brushing their teeth at noon, but they are. So, they're gonna think they're brushing their teeth at exactly the same time at noon. Well, they're not. Because Jean-Luc Picard is staying mostly stationary, he is perceived as brushing his teeth earlier than no wait he's James Tiberius Kirk. Because Kirk is on Earth and is basically stationary, uh, he's going to be perceived as brushing his teeth before Jean-Luc Picard, who is traveling in orbit around Earth. Uh, so, because a rotating object with mass, which is Earth, will drag along the space-time that is around it, which is, well, space-time, and what Jean-Luc Picard is coincidentally traveling through. So, time moves more slowly in gravitational fields than it does in the vacuum, which to me is highly self-explanatory. I don't know about you, but time moves more slowly in gravitational fields, like Earth or any space with gravity, than it does in a vacuum. So all that space between galaxies and solar systems and yeah, between galaxies there is just dark matter and emptiness. Really, there is no sun, so no gravity. So time is going to move very, very fast in those places than it does in solar systems and galaxies where there is actually a lot of gravity. Um, Energy is produced when an electron moves up or down in energy level, bringing us to E equals mc squared. So, E equals mc squared. It's a simple equation. It's energy equals mass times the speed of light represented as c squared. It's really kind of simple. So let's say my phone has a mass of 357. So it's going to be 357 times, and the speed of light is 299,747,400. Oh, 700,400. 742,000. I can't say that. And 458 miles per second. So it's going to be like that, and we're going to square right here. Okay? So that's going to be the equals. There we go. So we're going to reduce to 357 times 8.9845541 times 10 to the 16th power, which is a huge number. It's not as huge as Avogadro's number, which is 6.02 times 10 to the 23rd, but it's still pretty huge. So there's the simplified equation. Simplified equation. So now we're going to do simple multiplication, which will come out to be 3.2074858 times 10 to the 19th power equals E. That's the amount, there we go, that is the amount of energy in my phone, or whatever the mass has at 357 grams, which is hypothetically my phone right now. And mass can be converted to energy and vice versa. So we could take 3.2074858 equals x times 8.9845541 to the 16th. That equation right there, which is actually kind of sloppy. So let's come back to dedicated, to where I actually did it last video try. So we could do that. And then it's going to be that. And then it's going to be 357 grams, which actually I did the math. It comes out to be 356.9 repeating, which is 357. So the math is always, as usual, reversible. So that's all I have for you on the theories of relativity. And I hope you liked it. And I have a couple of things for you today. I have a question for you. How do you pronounce this word? Route or root? I never got that. And it's a regional thing. Do New Yorkers say it differently than proud Oklahomans? Or what? How do you say that? Are you in a different country and you don't have that word in your vocabulary? I don't understand it. It's confusing me. Second order of business. Name yourselves. Name yourselves. You are a fan base. I actually have a fan base right now. And you should name yourselves. I vote for the Inquirer. INQUIRER. The Inquirers. Because you guys should have inquiries for me, which are questions. Because I answer questions. And that brings me to the third order of business. State your question in the comments or on any of my social network outlets, which I will be putting annotations. Just connect with me. Connect. I don't know why I said the long O or a short O. I can't remember which one that is. But connect with me. Connect with me. It's not that hard to do. I'm pretty reasonable. So, alright. Bye. Bye. Say bye. Who is your favorite? Jean-Luc Picard or James Tiberius Kirk? That's my question for you. Other than the route thing. Bye.